Hello everyone, welcome to the biggest ideas in the universe. I'm your host Sean Carroll. You're here for the Q&A video for idea number 23, which was criticality and complexity, where we talked about how the world, which is governed by very simple underlying laws with just a few basic ingredients, can nevertheless become very complicated looking structures can arise in it. And I think that most of the questions fall into sort of one of two different themes. So I'm basically going to concentrate on those two themes. One of them is the relationship between complexity and entropy. There is a relationship, but it's not clear what it is. So this is a good sort of research level connection. The other is if you have one of these power law distributions, right? If you have a number of things as a function of size or whatever, and the number of things goes as the size to some power, there are mathematical technicalities associated with this. Like, what do you do at very, very, very small sizes, very, very large sizes? How do you calculate the average and stuff like that? So I'm going to go into some of those technicalities. It's not going to be like super duper highly technical, but it's important because it has to do with how the ideas that we talked about in the last video relate to the real world. And I think that the real world is important. So that's what we'll talk about. But first, let's go into complexity and entropy. I'm tempted to say complexity versus entropy, so why not say it? Why would I put it that way? Well, the general idea you should have in your mind is that entropy, which counts how many microstates correspond to a given macroscopically observable phenomenon in the Boltzmann way of talking about it. Those of you who are new here, we had a whole biggest ideas video on entropy. It increases in closed systems, right? The universe becomes higher and higher entropy. And roughly speaking, high entropy is boring. High entropy is simple in some very definable sense. If you have a box of gas, then you let the gas equilibrate, it's just going to be perfectly smooth. It's going to be the same everywhere in the box. If you have the universe with gravity, things are more complicated, okay? But if you wait long enough, if you wait to the far, far future of the universe, the equivalent of that equilibration of a box of gas is that the universe empties out. In a universe with a positive vacuum energy, like ours seems to have, the stuff that we have in the universe that makes it interesting, stars, planets, galaxies, eventually disperses away. And almost every region of the universe, almost every observable universe-sized region is just empty. So once again, very, very simple. So if you think of simplicity as the opposite of complexity, then the general tendency of the second law of thermodynamics, which is to increase entropy, should be to fight against complexity in some way. So you might want to know, why is there complex stuff in the universe if the general tendency is just for entropy to be increasing, and entropy makes things sort of just dissipate and be simple and not complex at all. So there are two sub-ideas here that I want to get into. One is, do power law distributions, and I'm going to not worry about the details of power law versus log normal or something like that. In fact, let's make it explicit that we're not worried about power laws. What we're worried about is scale-free behavior. So do scale-free distributions of something, we're not even going to go into what we're distributing, somehow maximize entropy in some sense, somehow, because clearly not in a very general sense, but we'll get into a sense in which they might possibly, okay? So remember, we talked about the fact that even if we don't agree on the once-and-for-all definition of complexity, we have this feeling that things that we would recognize and identify as complex have the feature that something is going on small scales and intermediate scales and large scales, okay? It's not just the same thing over and over again. It's not just one scale, one sort of level of interestingness repeated over and over again. That's not very complex, right? That's not very complicated. That's just kind of simple in its own way. So complex structures or organisms or systems have things going on at all scales. Now, a power law distribution is an example of that, but we also mentioned that there are things like log normal distributions, and there are other distributions that do a pretty good approximation of being scale-free over a certain regime. So that's what we're asking about. So does a distribution, so by distribution, let's change variables once again, change symbols. So let's say f of x, okay, is our distribution. And the reason why we're changing the symbols from what we did in the original video is I'm not specific about what we're talking about. This could be a number as a function of size, or a frequency as a function of rank, but it's some likelihood or number of times something happens versus some parameter that tells you about the scale of that system in a very, very general sense. And we're saying that f of x is given by, or at least proportional to, x to some power minus n. Okay, so we called alpha the power last time. We're going to call it n this time, just because n is a little bit less intimidating, right? It's a Latin letter rather than Greek. There you go. Most of us use the Latin alphabet. So if you have this kind of thing, what does that look like let's do it this way. On a regular plot, a linear plot, we have f of x versus x, and it's going to go like this if you have a positive n, so you have 1 over x to some positive power, or x to some negative power equivalently. And on a log-log plot, you have log of f versus log of x, and then it's going to look like a straight line with a downward slope, okay? And, you know, remember I did say that almost all the plots we were going to do in the last video were log-log plots, and yet when I plotted, I didn't plot, but I showed a plot of walking speed versus size of cities, and some people said, I don't understand like how you could walk with a negative speed, because they forgot that it's on a log-log plot. Remember what log looks like. If you have just some variable x and you take the log of x, at x equals 1, the log equals 0. At x equals between 0 and 1, log goes like this. And for positive numbers, log goes like this, okay? So the logarithm goes from minus infinity to infinity as x goes from 0 to plus infinity. So for x, between 0 and 1, the logarithm is a negative number even though x is a positive number. So when you saw negative walking speeds, you were really looking at negative logs of walking speeds in some units. All right. Anyway, so these are distributions, and we talked in the entropy video about the entropy of a distribution. So the entropy, in some sense, I'm not going to go into whose sense it is, Gibbs or Boltzmann or Shannon or something like that, but the entropy can be written as minus the integral of f of x times the log of f of x. This is the entropy of the distribution f for some distribution. So S of f integrated over dx. So this says take the distribution, multiply it by its log, integrate that, take the minus sign. Why the minus sign? Because f is often going to be less than 1 rather. So this thing in the integral is often going to be negative. So to get a positive entropy, you want that minus sign there. In particular, remember, if you think of f as a probability distribution, if that's what it is, then the probability of some discrete event is always less than 1 or equal to 1 at most, right? So this is generically, this thing in the integral is generically going to be negative, multiply it by a minus sign to get a positive entropy. Okay. And we said, so you might want to say, well, think of this. You know, we just said f of x is proportional to x to the minus n. We didn't normalize it. To normalize a function or a distribution means to divide by some constant number so that the integral of the whole thing becomes equal to 1. Right? You want the total probability, if that's what you're measuring, to be equal to 1. Or you can normalize it to some other thing. If you're talking about the number of people in a city, then you want to normalize to the total population of whatever system you're looking at. Okay. But we didn't do that here. We just said f of x is proportional to minus n, so you might want to normalize it or something like that. Then you could plug into this. And then you might ask, well, is there some sense in which these distributions, these power law distributions, are high entropy or low entropy, or what is the relationship between them? So remember that we also said for different kinds of distributions, let's say that we have a distribution that can only go from 0 to some x max. Okay, then here's f of x. And this is not the power law distributions. Now we're just talking about, let's imagine we have a distribution. And we said that if you have a peaked distribution like this, okay, this would be low entropy. This would be something where just by knowing the distribution, you know a lot about the system. There's some maximum value here for f of x, and probably the value of x in the actual system is very, very close to that because it's strongly peaked around that. That's low entropy. You know a lot about the system just by knowing the distribution. Whereas if you have a distribution like this that is more or less flat everywhere, that's a high entropy distribution, okay? High entropy means you don't know, just from knowing the distribution, where exactly x is. You don't have a lot of information about that. So, okay, what about these power laws? Well, I mean, it doesn't look high entropy at all, right? The power law kind of looks peaked at x equals 0 or something like that. You should be thinking about this plot right here in regular plotting space. So it certainly doesn't look like high entropy. So your initial idea, which is fine, is to say, look, if you have a system that is in a power law distribution of what's going on inside, then clearly it is not maximizing its entropy. Clearly it could be at even higher entropy, right? Because high entropy distributions are flat. But that's true as far as it goes. But there is a caveat there, which is that very, very often we have systems that are not closed, right, that are interacting with the rest of the world. And that means, and this is very, very complicated, like if you have a closed system, it's simple to know what to do. If you have an open system, there are many ways to be open. There's only one way to be closed or isolated. There are many, many ways to interact with the rest of the world, okay? So, for example, imagine a system in a heat bath. And we talked about this when we talked about entropy, etc. So you imagine that physically, here's some big box, and here's your little box with your system. And the big box is, you know, some photons or some gas or whatever at temperature T, capital T, okay? And then what happens is your system is allowed to exchange energy with the heat bath that it's in, so it's not closed. It can fluctuate slightly upward or downward in energy, okay? It still, if you let the system evolve, it still reaches an equilibrium distribution. And you might think, well, it's a maximum entropy distribution. That's what equilibrium means. But it is not this flat distribution. The distribution it reaches is the Maxwell-Boltzmann distribution. And it looks like this. I'm not going to give you the actual formula, but it looks like that. Okay, so here's f as a function of x, where x in this case is, you know, the momentum or the energy. In fact, it's the energy for the Maxwell-Boltzmann distribution. So in what sense is that Maxwell-Boltzmann distribution high entropy? Like, that's clearly not flat. It clearly does not maximize this actual entropy formula. If I had a distribution that just looked like that, it would have a higher entropy than the Maxwell-Boltzmann distribution has. So what is going on? What's going on is that the Maxwell-Boltzmann distribution maximizes entropy, S, the entropy, given the average energy of a molecule or an atom or whatever is in the system you're talking about is given by the temperature, okay? So this is a feature of this kind of system that can interact with the outside world. It doesn't make sense to just say, well, there's some initial conditions inside and we let them go, and we don't talk about the interaction with the rest of the world. The rest of the world can either put energy in or take energy out and is continuously doing so. So there's a constraint that you're at constant temperature, right? And different systems have different, you know, proportionality factors of a half or a third here or whatever, but it depends on how you measure. But the basic point is that in the box, the average temperature is going to be, the average energy is going to be given by the temperature, roughly speaking. But that allows for fluctuations around that. The total energy inside the box can go up and down. And so what you want to do is just not maximize the entropy inside the box full stop. You want to maximize the entropy of the box subject to the constraint that the average energy is given by a fixed number. And that gives you the Maxwell-Boltzmann distribution. It's very possible that either Maxwell or Boltzmann actually derived the distribution this way, probably Boltzmann, but I'm not sure about that. The point is that once you start saying subject to a certain constraint, I'm going to maximize the entropy, then you can get distributions that are not flat and yet are in some sense maximizing the entropy. And the Maxwell-Boltzmann distribution does that. So you can ask yourself, does f of x, that's a terrible f, isn't it? I'm getting too excited by statistical mechanics. Does f of x proportional to x to the minus n maximize the entropy subject to some constraint? And if so, what kind of constraint is it? And the answer is, I'm not really sure. Or rather, the answer is yes, you can invent constraints such that when you maximize the entropy of a distribution subject to those constraints, you get a power law. Okay, that is a true statement. What is not clear, certainly to me, and I don't think to anybody, is are the kinds of constraints that you can choose to make that happen relevant to the systems that you're actually thinking about. Remember, I tried to make this a theme of the complexity video itself, that it's one thing to show that a distribution has a certain form. Okay, it's a completely other thing to understand the physical mechanism behind that kind of form. And so if you just want to know, if you have this target in mind ahead of time, I want to get a power law because I see power laws in nature a lot. And I think that systems try to maximize their entropy, which, by the way, I mean, they do. And I'm not trying to downplay that. The philosophy here, the physical intuition that we're working on is that given some constraints, if you know what's happening in terms of the exchange of information or heat or whatever between an open system and its environment, given those constraints, it's perfectly natural to think that the system will work to maximize its entropy. The point is, however, that there can be more than one way to actually put on such constraints. And, you know, this is the homework that I did for this Q&A video. I Googled it, maximize entropy with power law distribution. I've done this before in my life, but I've sort of forgotten the results because the results are, there are different papers claiming that if I put on this constraint or that constraint or this other constraint, I can maximize entropy and get a power law distribution. So there's two possibilities for what's going on here. One possibility is that in the real world, when you see power law distributions, they are maximum entropy for completely different reasons, right? Like different power laws might be taking this temporary equilibrium form of a power law, let me say that more accurately. It might temporarily be true that for a certain open system, its equilibrium form is a power law rather than Maxwell-Boltzmann or just flat. And for another system, it's for a completely different reason, right? And that's completely possible. The other possibility is that there's something deeper that we don't know or that we haven't pinpointed, or at least that I have not been able to figure out or find, which makes it all universal, right? Which says that here's the reason why you over and over again get these complex power law structures. I'm skeptical about the latter just because, you don't always get power law distributions. You get log normals, you get other things like that. And so you don't want your purported grand explanation to be too good, that it rules out the possibility of other things that we actually observe in nature sometimes. So I like the idea of saying that for this or that system, we ask, why does it have this power law form? And we provide an explanation. So it's a different kind of explanation than what we had before. What we were talking about before in the original video were generative models, right? You start with a distribution and then you act on it in some time-evolving kind of way, like a preferential attachment model where people have a certain probability of going to a certain city or something like that. And then you generate a final distribution by doing that over and over again, okay? This is a whole different philosophy of generating a distribution. This is saying, I have a system, I let it equilibrate subject to some external constraints, and I find that it ends up in a power law, okay? Different words than something like the generative models would have. But maybe there is underlying systematic things that make those two things match up in the right circumstances. All I'm saying is that I don't know right now, and I'm not sure it's known. I suspect that the landscape of complexity is complex, and you shouldn't be overly eager to say that every single complex system has the same origin for its structure on all scales. But I'd be happy to be wrong about that. I'm sure there's also some universality in some of the features. We just don't know what they are. Did I say everything? Oh yeah, the other thing I wanted to say about that was there's another consideration that again I'm not going to be very helpful about to clarify. There's the idea that you maximize entropy versus entropy production. Okay, so remember, we're dealing with open systems now. So a living being or an ecosystem or a computer, they generate heat, right? Your laptop gets hot if you put it on your lap, despite the fact that it's called a laptop. Why? Because it's doing calculations, it's generating heat, it is increasing the entropy of the universe, it is producing entropy, okay? So another way of asking this question is not, maybe the principle, the dynamical principle that is going on is not the system maximizes its entropy, but that it either maximizes or minimizes, depending on the circumstances, its entropy production. And so maybe, in the right circumstances, either we're talking about a complex system that wants to be efficient, like a biological organism, right? That, evolution guides us in directions where we use the energy that we take in the most possible efficient way, and you might interpret that as minimizing the entropy production rate. Or conversely, you might say, well, there's different channels for different reactions to go through, and entropy wants to increase. So if you can find a channel for a reaction to happen in that maximizes the entropy production, then that's favored for some reason, right? So all of this, you see why this is complicated. If you go and Google maximum entropy principles, one of the things you will find is there are also minimum entropy principles. And I'm not a super duper expert here, so I think that there are experts who have strong opinions, but I gather their opinions don't agree with each other about the best way of thinking about these different things, which is, again, a reflection of the fact that the whole field is a little bit pre-paradigmatic. We haven't yet decided what are the spherical cows that we should focus on in this game. Okay, so that's one thing I wanted to say about complexity versus entropy. Do complex systems in some sense maximize the entropy? The answer is maybe. In fact, I would go so far as to say the answer is probably, but it's still a lot of work to figure out in what sense that actually is. What are the constraints you have to put on the system to make that happen? The other question is, again, this is still under the rubric of complexity versus entropy. The other question is why do complex structures, let's say does complexity evolve? And I don't mean evolve over time once it's complex, but how do they come to exist in the first place? Again, this is related to the fact that if the second law of thermodynamics is true, everything is just increasing entropy, then why in the world do you stop along the way to be a complex structure? This is a relative of the creationist argument against evolution, right? That says the second law of thermodynamics just says entropy is increasing, yet we have all this wonderfully complex biosphere on Earth. You have violated the laws of physics if you believe in evolution. So there's two answers to that argument. One is that's a very bad argument because the biosphere is not a closed system, right? Entropy only increases in closed systems. It doesn't necessarily increase in open systems. Otherwise, you could not put champagne in your refrigerator and cool it off. And that's usually the answer that's given, and by itself, that's perfectly good. But that doesn't actually say why it is true that the complex structures do arise. What that argument says is that it doesn't violate any laws of physics for complex structures to arise in the ecosystem, but it doesn't say therefore they will, it just says it doesn't violate the laws of physics. You might ask for more than that, right? You might say, well, why? I mean, is it necessarily true that complex structures would arise, or is it likely, or was it a rare fluke, or what's going on here in something like the biosphere? Okay, so for this, again, I'm going to beg your indulgence because I've actually written a paper about this, and I want to tell you about what was in that paper. And, again, I do this all the time, but it's my video series. So, of course, I'm going to tell you about my papers. Not just because I think my papers are the best, but because I try to answer the questions I'm interested in, right? And so those are going to appear in the videos. So how and why does complexity evolve is a question I addressed in a paper with Scott Aronson, Lauren Willett, who has the same last name but is not related to my wife Jennifer Willett. And so we published a paper, and actually it was a couple of people pointed out that we made a mistake, and so we fixed it, and so this is very embarrassing, and so this is why I love all you folks, so I'm telling you this embarrassing fact. It's been years, and we have still not submitted the revised version of the paper to the archive. We have a revised version that is correct, and it's still not in the public domain. I'm sorry about that, but I hope to get it there quickly. Brett Burness is one of the people, a postdoc, who helped us figure this out. And I'll explain to you what I mean. Here is the paper that we wrote. We examined the famous example of a cup of coffee. Okay, so I haven't planned out how to best draw this, but anyway, here's the cup, and what we imagine is that here, yeah, let me see, can I do this? Here we have cream, and there we have coffee, okay? So this is the cream, and we layer it on the top, and you have coffee on the bottom. And this is a low entropy configuration, okay? But if you stir it, the entropy goes up. Now, stirring it is not quite fair because then it's not a closed system anymore, but we're going to ignore all of those. That's not the issue that we're dealing with here today. We're dealing with a slightly different issue. What we know is that if you let time go by, okay, and you do stir it with a spoon, then what you will get is, oops, I gotta draw my cup in a consistent way here. Here's my coffee cup. And let me make this cream here a little bit brighter because it's thicker, okay? Look at this, getting good. And then over here, when everything is mixed together, we have cream and coffee all mixed together, okay? So this is clearly low entropy. All the cream's on the top, all the coffee's on the bottom, segregated. Here, once everything's mixed together, it is clearly high entropy. But you notice that there's no complexity anywhere here in these two pictures that I've drawn. If you just, again, don't worry too much about the detailed definition of complexity and you just look at the pictures, this is simple. All the cream's on the top, all the coffee's on the bottom. That's all the information you need to know. So you're tempted, and it's okay, to use a sort of Kolmogorov definition of complexity. Remember, the Kolmogorov complexity had to do with the shortest algorithm that you would need to write to print out a number. So if you think of the cream and the coffee as an image, like, you know, pixelate it and make a file, a JPEG on your computer, could you make a computer program to print out the pixels of this image? Well, yeah, you just print out a whole bunch of white pixels and then a whole bunch of black pixels. That's it. It's a very simple, short program. Likewise, over here in the high entropy state, it is also simple. You just print out a whole bunch of gray pixels or brown pixels or whatever it is. They're all mixed together, okay? So there is clearly, and again, we haven't defined exactly what we mean by entropy in this sense yet, but in this sort of casual, I know it when I see it sense, it is clear there is no strict relationship between entropy and complexity, right? Here you can have very low entropy and also low complexity, high simplicity, if complexity is the opposite of simplicity. But you can also have very high entropy and be simple, okay? So one of the mistakes that the creationists make is to conflate low entropy with high complexity. That's not exactly the same thing. Very, very, very low entropy is always simple. And very, very, very high entropy is always simple. What's interesting is in between, okay? So if I move this little arrow down, actually let me move it up a little bit, and then imagine that I actually took a snapshot while I was stirring the cream into the coffee, okay? Well then, I wonder how clever I can be about this. Probably medium clever. So then, you know, you have some cream at the top, but it also sort of gets mixed in a little bit, right? And you begin to see this is a step along the way of when you're stirring the cream into the coffee, right? You see swirls and tendrils, you know, things that look like galaxies in the coffee cup, right? If you're astronomically inclined. So this is medium entropy. And again, by the standards of, well, I just look at it, and I ask myself, you know, how long would the description be if I tried to describe it? This is complex. In fact, you could kind of imagine that there is structure on all different scales inside that coffee cup. There's tiny little swirls and there's big swirls, etc. On both of the sides of low entropy and high entropy, there was not structure on all scales, right? It was very homogeneous over large scales, but here there's something going on at all different scales. It looks complex. So what this means is that there's not a monotonic relationship between entropy and complexity. So if you think about entropy going up and complexity, so imagine this is complex and this is simple, okay? Then what you get is a curve like this. That complexity can get big when entropy is medium-sized. And you can actually show that when entropy is very, very low, it's always going to be simple. When entropy is very, very high, it's always going to be simple. So it's possible, it's allowed for entropy to go up when you're on the, for complexity to go up when you're on the road from low entropy to high entropy, but it's not necessary. This would also be an allowed curve, or this would be an allowed curve, right? These are all different ways that entropy and complexity can be related. Jim Crutchfield, who's a complexity scientist at UC Davis, has referred to this curve, entropy versus complexity, as something that is rediscovered every 5 years. So Scott and Lauren and Brett and I rediscovered it once again, but what we did, what that was a little bit different, is that we plotted it versus time, okay? So if this is just the general formula or general behavior of complexity versus entropy, well, you know that there is a monotonic relationship between entropy and time. That's called the second law of thermodynamics, right? So entropy just goes up like this, whereas complexity can go up and then go down. Okay. So this is a slightly more sophisticated response to the creationist critique about evolution versus the second law of thermodynamics. Not only is it completely okay for complex structures to evolve as entropy is increasing, but in some very natural sense, you need for entropy to be increasing if you want to make complex structures. That's when complex structures happen, when you're out of equilibrium, when you have the second law of thermodynamics, when entropy can be increasing. If you think back up here at these systems that are open, exchanging information or even matter with their environment, if you think about the models that we talked about where people actually enter cities or leave them, or there's a sand pile and you're dripping new grains of sand onto the pile, all of these are out of equilibrium systems. That's a fundamental fact about them. So it's sort of the creationists have it exactly backwards. You need entropy to be increasing to get and to maintain these complex structures. Okay. But this still doesn't quite say that they do happen. I mean, that's the lesson of these different curves here, that complexity is allowed to evolve, but it doesn't necessarily. So the other thing to say, by the way, is that this is not just cream and coffee. I gave you that example, and what we did in our little computer simulations is a sort of cellular automaton model for cream and coffee mixing together, the coffee automaton, we called it. But other systems have exactly this behavior. Think about the entire universe, right? When we did the cosmology video, we talked about the fact that the early universe was a very simple place. It was hot and dense and smooth. That's all you need to know. That's the Kolmogorov complexity shortest algorithm. Hot, dense, smooth, rapidly expanding. There you go. That's the universe. The late universe, very, very simple, right? Cold, dilute, still smooth, okay? That's the very late universe. It's still very, very simple. It's now at the intermediate stage of the history of the universe where things are lumpy and changing dynamically, and something is happening on all different scales. Now is when the universe is complex in some very definite way, okay? So the universe obeys this kind of going up and going down plot here of complexity over time. So that's a nice thing to keep in mind. Okay, so, but we didn't just state these things. We tried to quantify it. Look, this is one of those cases where, honestly, this is most of the content. These pictures, and once you see it, everyone goes, "Oh yeah, okay, sure, that makes sense." But here's a little inside scoop on how science works. You can't just write up a page or 2 pages and draw these pictures and submit it to a journal and say, publish me. Like, no one would care. Like, people would say, "Come on, That is not enough. There's something in science called the least publishable unit, or something in academia more generally. Like you have to do a certain amount of work, put a certain amount of effort into it to actually get something published. And getting published papers is the currency of the realm in academia. So we wanted to say, like, okay, what could we say about this? Could we derive theorems about it, or get some numerical results, or what could we show? So we did these little computer simulations of cream mixing into coffee, and so one thing we hit automatically is you want to plot complexity versus time. Entropy versus time is easy, that you can calculate, but you need a formula for complexity, right? And that's exactly what I've been saying. Like, I'm not going to tell you the formula because we don't have a formula, right? So if you want to plot it, you need a formula. So what do we mean by complexity in this case? We invented something called the apparent complexity. So first, let me remind you of the Kolmogorov complexity. I hope I'm spelling his name correctly. Kolmogorov complexity is the shortest algorithm. I'm not going to write the whole thing, but it's the shortest algorithm that will print out the system, the string or whatever that you're interested in. So we have that because we have an image of where the cream is, where the coffee is. Despite calling it a coffee cup, we did a two-dimensional automaton, so really, literally, it's just a two-dimensional image. So the shortest algorithm that will print out the JPEG file that will make that image. Okay. Here's a problem. Here's a cute little problem about using the Kolmogorov complexity. There's two problems. Problem one is that it doesn't actually capture what you care about. Because if you think about it, remember, this is exactly the problem that we had that I mentioned about the Kolmogorov complexity in the case of strings, is that a random string is super duper complex in the Kolmogorov complexity. So if you have this kind of thing over here where you have all the coffee molecules and cream molecules are exactly equally distributed, then it would be very low Kolmogorov complexity. But if you had tiny fluctuations, right? If you typically had from one pixel to another a completely different value, then your Kolmogorov complexity would be huge because you need to specify every single pixel. Right? So that's a little bit not exactly what we want. We want something where a random number counts as low complexity, right? A truly random image, just random amounts of little tiny pixels should be kind of a white noise thing, but we want to sort of average over a certain size, right? Like we can't see every individual atom in the coffee and the cream. So in some sense, we want to coarse grain. And therefore, we invented something called the apparent complexity. The apparent complexity that we invented is basically just the coarse-grained Kolmogorov complexity. So what that means is we take this image that we have of cream mixing into coffee, we average over a certain, size of a certain number of pixels, and then we ask about the Kolmogorov complexity of that to within some error bars or something like that. So in that case, if you have something which is just random numbers, they will all average out, central limit theorem, right? And therefore we get a low Kolmogorov complexity. So indeed, we checked the apparent complexity for images like this is low for cream and coffee being completely separate, high for them being completely mixed together. Sorry, low for being them completely mixed together, and high for the swirls and all that stuff. The other problem with Kolmogorov complexity is that it's uncomputable. And this is not actually relevant to anything that we're talking about in complexity, but it's a cute fact that maybe you should know. You literally, in principle, cannot calculate the Kolmogorov complexity of a string. If someone hands you a string, if someone hands you an algorithm, then you can figure out how long the algorithm is. But if someone says, here's a string or here's an image, what is the shortest algorithm that can print it out, you don't know. You can never know. And why? Well, it's because of the halting problem, essentially. I'm not going to go into this. But there is a known problem in computer science. Alan Turing showed that if you ask the following question, given a computer program, okay, can you tell me whether it will ever halt, ever stop running or not, right? You know that if you've ever done any computer programming, there is the infinite loop problem. You can just get caught in a loop and cycle around over and over and over again, okay? And that's bad. So you might think that you should just be able to look at a computer program, and if you're a very, very good programmer, you should be able to notice whether there is an infinite loop stuck in there somewhere or not. So Turing proved that in principle, in general, you cannot ever do that. And the way that he proved it is basically he was able to find a way of essentially writing a computer program. So if you have one algorithm that will answer whether another algorithm halts or not, okay, then he figured out a way to make the other algorithm essentially say, okay, if this other algorithm says I'm going to halt, then I'm not going to halt. And if it says I am going to halt, then I won't. Okay? So it's very much in the spirit of Gödel's incompleteness theorem. Kurt Gödel managed to write a statement in mathematical number theory that was equivalent to saying, I cannot be proven true. And then if you can prove it true, your system is inconsistent. And if you can't prove it true, then there are true statements that cannot be proven. So this is a program that can't be evaluated for whether or not it halts, according to Turing. And the model of complexity, well, how would you try to evaluate it? If someone gives you an image and says, okay, find the shortest algorithm that will do that, you might say, well, I'm just going to keep making up algorithms from the shortest algorithm I can write to the until I get to the point where I know that I can output that image. The problem is you might hit an algorithm where you can't know whether it halts or not before you get to the algorithm that prints out your image. So again, very roughly speaking, I hope the mathematicians and complexity theorists forgive me. But anyway, you can't compute the model of complexity in principle. What you can do, it can be estimated. So you can get a very good approximate value for the Kolmogorov of complexity. And the reason I mention this really is just because it's funny. How do you figure out the Kolmogorov of complexity of something? Well, you know, we have algorithms that take images like these and try to compress them, right? In fact, in other words, we essentially have tried to approximate the action of, given an image, find the shortest algorithm that'll print it out, right? Those are called compression algorithms. So when I say, imagine the JPEG file on your computer, the JPEG is an algorithm that, given an image, tries to shrink it down to the smallest size that it possibly can, then still sort of faithfully reproduce it. And so if you want to know, if you have a computer algorithm, you know, automaton that models cream and coffee mixing into each other, and you want to know, given the final result or given some intermediate result like this one, so, you know, here you have an image, how complex is it, okay? You just actually put it into JPEG as a file, and you ask how big file size is. That's the apparent complexity estimator that we can use, and we did use, and it works very well. We tested that it works very well. Okay, that's just cute and fun. So what are the results? What do I mean by the results? I mean, we built a computer program that models by little pixels cream and coffee, and then has some dynamics where the cream and the coffee can mix together. And we let it mix all the way until it was all mixed together. And then in this way, we estimated the apparent complexity of the images along the way, and we plotted them, okay? And what we find is actually kind of really interesting. What we find is the results. And this, I think this is new as far as I know, because even though people have known about these curves before, they haven't really worried about the time evolution of them. So the question is, what kind of dynamics gives rise to complexity? So what is the difference between the dynamics that gives rise to this kind of curve that goes way up and way down versus this kind of curve that just remains low? And so we, you know, what we did was we said, well, what if just the cream and coffee move independently? They don't even talk to each other, okay? Then you would expect they just diffuse gradually into each other, and you shouldn't get a lot of complexity. And we verified that's true. You don't get a lot of complexity if the cream and coffee are moving independently. Then we said, okay, let's imagine that randomly different cream and coffee molecules can switch places. If they're nearest neighbors, they can just sort of switch back and forth to each other. Then eventually they will mix together. And we hoped, and we actually said in the original incorrect version of our paper, that complexity does develop in that case. But then we later realized we were wrong. And what's going on? We were actually able to show, or I guess Brett was able to show, that the local interactions never give rise to complexity. So local interactions don't produce complexity. By which I mean, if you sort of imagine zooming in this figure, and imagine that you have interactions that just take, one pixel here and one pixel there, and let them flip or let them not flip or whatever, nothing like that ever gives rise to complex structure in the coffee cup automaton. And then we were depressed for a little while, but then we worked harder, and we found that interactions with long scale correlations do produce complexity. So rather than just letting one little pixel and one other little pixel switch, what we said was if you could sort of coherently have an arbitrary sized box that moves as one. So you say that you pick a random sized box, here's a random sized box, and it randomly shifts either up, down, or left, right, or whatever. And we call that the Tectonic Model, okay? That does give rise to complexity. And just to show you the results, I'm going to try this again, importing a picture. Let's see if this works. So this is one of the results we got. So you see that this is complexity up here, our apparent complexity versus time steps. So the red is this diffusive model where the cream and coffee don't even notice each other. The blue, the tectonic model, is where there are these coherent shifts of blocks of different size. And then this is the complexity. You see the complex structure does evolve like a fractal-like distribution, power law kind of distribution for the cream and the coffee. Evolves and then it goes away, okay? So I think that there's a lesson here. I think this is just like a tiny little beginning of a bigger project. The lesson is that the kinds of dynamical interactions that give rise to complexity have to themselves operate on long scales, right? It can't just be individual nearest neighbor kind of things. That's perfectly plausible in the real world. We have, gravity and electromagnetism, both of which act over very large timescales. There are subtleties and footnotes there. Like you can act individually over very small distances, but then if you carry information a long way and act somewhere else, that might count just as well, right? So it's not quite a theorem that says you need long-range interactions, but you need information to be shared over large regions in order for complexity to arise. That's not quite a theorem either. I wish it were a theorem. That would be a nice thing to make more general. But anyway, this was all a very, very long-winded way of saying that you should not be surprised that in the process of entropy increasing in the universe, complex structures arise. The laws of physics, given the laws of physics and the fact that the early universe had low entropy, to say that complex structures happen very naturally without any planning, without any arrangement, is the most natural thing in the world. Now, these are like really simple, dumb complex structures, literally just a complicated looking picture of cream and coffee coming together. But you could imagine very straightforwardly that more interesting structures follow the same pattern. Of course, there's one pattern, there's one structure that everyone cares about, which is life, right? What we'd like to know is if the origin of life is somehow connected to this story. If the fact that somewhere 3.5 billion years ago on the Earth, certain complex chemical reactions came together in the right way to form the beginnings of life, what is the connection of that fact to these statements about entropy and complexity and long-range interactions and power laws and all these things? Many of us believe there is a connection. I think the connection is still very obscure, what it is. Most work being done by origin of life researchers are done by either biologists or geologists or chemists, okay? The physicists are beginning to horn in on the game, and physics alone is not going to do it, nor math or computer science alone is not going to do it. You're going to need biology and chemistry and geology, for that matter, planetary science. But there might be some general principles that help us understand why life began, not just the specific exact way that it began, but was it likely? Was it a rare fluctuation? Is it the kind of thing that happens all the time? These are things that I think are answerable questions to which right now we don't have the answers at all, but I think that we're going to be able to get there. Okay, the other thing I wanted to talk about were, some details, some technical details about power laws. Because people correctly asked some perceptive questions about power law distributions. Because, again, this is a little bit insight into how science goes, right? We say words like power law distributions, but there's a question, like, how seriously do you take that? Like, how much can you extend the power law across all the different scales? Or, did you only ever mean it was approximate or within some regime or whatever? These are all crucially important questions that we should actually think about. So, think about our power laws again, okay? So let's do this on just a linear plot, so not a log-log plot. F of x goes down like this, as a function of x, and so this is x to the minus n, okay? And we're going to have to do some calculus, okay? Let's note one problem right away, that as x goes to 0, f of x blows up. If n is a positive integer, a positive number of any sort, then f of x becomes infinite. So there's already a problem, which is, are you telling me there needs to be an infinite number of infinitesimally small things in my power law? And the answer there is, well, no. You're not really supposed to take it seriously as x goes to 0, right? Like maybe at some value, it begins to be well approximated by a power law, whatever this distribution is, city sizes or whatever. Like if your distribution is city sizes or lengths of words or something like that, there is a smallest city size, one person, and there's a smallest word, one letter, etc. So you shouldn't extrapolate beyond where it makes physical sense to do so. But there's another problem, which is, what if we wanted to calculate the average? What is the average value of x in this power law? There's different notations that people use, but I'll just say average value of x. Well, one way to do that is we first need to do the integral of f of x, right? Get or normalize it or something like that. So we talked about doing integrals before, we've talked about calculus, and one of the things I've shielded you from is that, if all you knew about calculus was what you heard in these videos, especially video number 2, which was on change, you might think that calculus is not that bad, some symbols and some concepts, but how hard is it? Why are people always complaining? Of course, if you took a course on calculus and did problems, then very little of your intellectual power is devoted to the concepts, and a lot of it is devoted to the rules for manipulating functions and taking their derivatives and taking their integrals. And those rules and those procedures can be very complicated, okay? So I've saved you from learning all those rules, but now we're going to have to do one. And I'm just going to do the simplest one. Remember, we talked about the fact that doing derivatives of functions is relatively easy, doing integrals of them is relatively hard, but for functions of this form, f of x is x to the minus n, it turns out to be easy in both cases. So if we have f of x equals x to the minus n, what is the derivative of f with respect to x? Well, the answer is you take that exponent, in this case minus n, and you pull it down and multiply. So this is minus n times x, and then you remove 1, you subtract 1 from the exponent. So it's x to the minus n minus 1, okay? That's it. That's the formula. That's the derivative of this function at any one point. What about the integral? So the integral, well, the crucial thing about the integral is the integral of f of x dx. When you do the integral of a function, it had better be the opposite of doing the derivative. That is to say, if you do the integral of the derivative or the derivative of the integral, you better get back the original function. So if the exponent goes down by 1 when you differentiate, it better go up by 1 when you integrate. So you know that this is going to be proportional to x to the minus n plus 1. And then you know that if you differentiate the right-hand side, you better get rid of whatever numbers you have outside. So you're going to bring down minus n plus 1. So you better divide by minus n plus 1. There you go. That's the integral. And therefore, you can check. If you take this thing on the right-hand side, x to the minus n plus 1 over minus n plus 1, and differentiate it, you should get this answer. You should get x to the minus n back. Okay? Good. Except, there's one exception. When f of x equals x to the minus 1, when n equals 1, then look what happens. Well, it's not easy to see what happens here, but when n equals 1, you just get x to the 0 here, and sort of you stop this chain of going down. If you just differentiate, 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 or integrate and integrate, you should be able to go up and down by integers, but you can't if you hit 0 in the exponent at any one time. So it turns out that the integral of x to the minus 1 dx, so that's n equals 1 in our notation, is the logarithm of x. It's a special case, okay, but otherwise this is true. So if you want to know, what is the, how do we normalize this distribution? How do we take the integral over everything here? Well, when you integrate, here's another trick for not a trick, a fact about doing integrals. Let's say you integrate between two numbers. Let's say this is a and this is b. Remember, the integral is the area under the curve, okay? So if you integrate between a and b, we write that in this notation. Okay, you integrate from a to b. And the answer is, so in fact, let me just plug in that f of x equals x to the minus n. Well, it's this, x minus n plus 1 over 1. So let's write over 1 over minus n plus 1. But then we plug in x equals b into this formula. And then we subtract from that what we get when we plug in x equals a from this formula. So we get b to the minus n plus 1 minus a to the minus n plus 1. And one way of thinking about this is, I'm not sure if should I do this in another color or not. Let's see if I can do it in another color. I haven't used this magenta yet. The integral up to b is sort of everything here. And the integral up to a is sort of everything here up to a. And then you subtract off the integral up to a from the integral up to b, and you get just the white area in here, which I'll make even whiter, okay? You get just this area, which is what we want. That's what we're looking for. Okay, so that's nice, but now let's see what happens here. Let's take, if f of x equals x to the minus n, let's take n equals 2, right? Then minus n plus 1 equals minus 1. So the integral from a to b, x to the minus 2 dx equals 1 over minus 1. So I'm just going to write that as minus 1. 1 over minus 1 is minus 1. I think we agree. Times b to the power minus 1 minus a to the power minus 1. Okay, but if you thought you were taking your distribution too seriously and let a go all the way down to 0, then a to the minus 1 is infinity. And that's bad, right? That means that, there is the integral under the curve is infinitely big. And that doesn't sound good. That doesn't sound like what we want at all. Because remember, the curve represents something real, the number of cities or the number of people or the number of elephants or something like that. So to have it be infinite is just bad in some way. Likewise, if you have, let's say, n equals 0.5. Okay, so you get an integer below 1. Then minus n plus 1 equals 0.5. Okay, and your integral from a to b of x to the minus 0.5 dx equals minus n plus 1, so 0.5, 1 over 0.5, in other words, 2, times b to the 0.5 minus a to the 0.5. So, okay, that's good. A can go to 0. 0 to 0.5 is just 0. That's no problem. But B, you're supposed to be able to take up to infinity. You should be able to, if you just believe this curve for any value of x. And then B, infinity to the minus 0.5 power is infinity again. So I still got infinity for the integral of this function. And finally, I'm not going to go into it, but if n were exactly 1, then I would have this exception, and I would have the integral of x to the minus 1 dx, which is log x. And if I look way back here at what the logarithm does, where's my logarithm function? The logarithm is minus infinity at 0 and plus infinity at plus infinity. So it's the worst. It's infinity in both directions. So the point is that these kinds of curves are not normalizable. There is no such thing as the total area under the curve, or rather it's infinite, technically. You know, it's whatever you want to call that, a number or a limit or whatever. It's not just a finite number. And therefore we can't, take the average of it or anything like that. There is no average value. Someone explicitly asked, like if I have some physical thing like avalanches or meteorites or whatever described by this power law, and I want to say, okay, what's the average? I don't think I can get it. And the answer is yes, you can't get it. There's no such thing as the average value in this kind of distribution. So what's going on, and what are you supposed to do about that? That's the question I wanted to address in a very kind of slightly unhelpful way. But let's do the log-log plot again. Okay, so here's log of f versus log of x. And we're saying that, okay, it's a straight line, but you can't do the integral over the whole thing. You can't find the average, things like that. You can't treat it too seriously. But the answer is you can't treat it too seriously. That's what the answer is. So remember, in the real world, you got to keep in mind the difference between the real world and spherical cow land, okay? Like the exact power law that you extend to x equals 0 and x equals to infinity is clearly an approximation, clearly a spherical cow, clearly ignoring some important features of the physical system. In the real world, you have some data points, remember? And the data points might be very, very well approximated by a power law, but you should know that you better not extend them too far to the right or to the left, because whatever were the approximations that you made are going to cease to be valid. And the reason why we couldn't do an integral under this curve, why we couldn't normalize it, why we couldn't find the average, was not because of what's going on here in the power law region, but because of what's going on at the tails, either at 0 or at infinity, right? And the answer really is don't take the rules seriously there for one reason or another. So in real-world applications of this kind of way of thinking about complex systems, you have to not only say, I have a power law, but you have to say, between whatever values of x, I can actually verify the power law is real, and I shouldn't believe it above that or below it. And the reason why that's crucially important is because, as we said before in the original video here, it's very often the case, these power laws have the property that they feature a lot of events, or more events than you might want to believe in, at very, very large values of x, right? Like way more than you would get with a normal distribution, with a Gaussian. Even way more than you would get with a log normal or something like that, okay? So when you have rare but crucially important events, pandemics maybe, avalanches, solar flares, whatever they are, earthquakes, it's crucially important to know how far we can extend our belief in this power law-like behavior to values of the size parameter that we haven't actually gathered a lot of data about. That's why, in recent, it's not why, but it is closely related to the fact that whether it's climate or pandemics or whatever, you might have noticed that in recent years, in the last 10 years, there have been a lot of events where this is supposed to be a 1 in every 100-year event. And how many times, how can you get 1 in every 100-year events every 2 years, right? Well, there's something off about your extrapolation of the power laws to very, very large scales. So I'm not going to tell you what the remedy is. I'm not going to tell you how to deal with this other than to be cautious, right? Other than to know what your uncertainties are, to know the, if any of you happen to enter into the game of predicting the stock market or avalanches or whatever, know where to believe your extrapolations into unknown territory and know where to be skeptical of them, right? This is just a crucial feature of how to do science correctly. It's just that in this sort of power law type behavior, it becomes even more necessary. And if you want to know something like, okay, for meteorites, for avalanches or whatever, what is the average size? I'm not sure if there's an algorithm for answering that, but my answer would be try just doing the calculation, taking the power law seriously where it's allowed to be taken seriously. And this is something, again, that's sort of vaguely reminiscent of what we talked about with the renormalization group. In other words, you put cutoffs, okay? An infrared cutoff at large distances, an ultraviolet cutoff at small distances, and then you calculate things, and everything is cut off. You should get finite answers for the average and for, you know, the total number and things like that. And then ask yourself, do those quantities depend sensitively on your cutoffs? And if they don't, then it's okay. Then you've succeeded. Then you've found a good, reasonable answer. But if your answers depend a lot on your cutoffs, that means that you don't know what's going on. You don't really know the true physical situation. It's not quite accurately being described by this power law that you have. So I have no more words of wisdom than that. This is part of the adventure of doing science, that it's fun to push around the equations. It's much harder to understand the real world. Both of them are useful. I hope that over the course of these videos, you've learned a little bit about both kind of techniques.